All right, so this is going to be an extension of the continuity notes that we talked about yesterday. I had mentioned earlier that I was going to do this particular page, it's the back side of what we were looking at. I'm going to skip over that. In this, what you would do is you would be identifying where a discontinuity would occur. So you'd be mentioning, for instance, here you would state that the discontinuity would occur at x is equal to 2. From that, you would be asked whether that is removable or non-removable. So your question would be, is this an asymptotic or a point discontinuity? And what I would have you do is factor out your problem just like you would in a standard problem where you identify a hole. And when you do that, just like the question that I had shown you earlier, you would wind up stating, oh, well, this is going to be a point discontinuity. There's a hole when x is equal to 2. Go ahead and we'll write that down. And if that's a hole, then this is going to be, this is 1, 2, this is going to be a point removable discontinuity. Which is kind of what 3 is asking. Identify and remove as removable or non-removable, and then they would ask you to sketch that. So all in your sketch you would be asked to do is to realize that, hey, this is a graph, has a y-intercept of 2, and at 2 it would go through 2, 4. If you need help remembering how to deal with the holes, let me know, and I will gladly assist you. There's that one question. I'm going to save the other 3 as for you to deal with. C in particular is an interesting case. We may look at that tomorrow in class. So the ones that I am interested in is how do we actually use the definition of continuity, the idea that a point exists, a limit exists, and the point and limit must be the same. How do we use those to examine whether a function is going to be continuous or not? So what we have are 3 piecewise functions here. And for each of these 3 piecewise functions, we're going to do this. Now, piecewise functions. Step 1, always double check to make sure that it's continuous within its domain. And what I mean by that is this is a quadratic function. There's nothing interesting to the quadratic function. It just is what it is. It's always continuous. This is a linear. In fact, looking at the notes, well, there is one. Down here, we're going to get into an interesting case because you'll notice that there's a discontinuity for this function right here when x is equal to -1. Now, this is not going to be so. Now, if the equal sign was shifted down here, this would make things really interesting because that would mean that there would be no, the point wouldn't actually exist since that's where the discontinuity exists. We would say the point doesn't exist, but that's not the case, so we'll see how that works. I apologize. So what do? We look at the problem, and first thing we have to do is we have to identify, is there a point? Yes, there is a point. We have to do this. So we take a look, and we have to find the f of 1. Well, to find the f of 1, I identify which one has the equal sign, and I realize that that's going to be 1 squared minus 3 is -2. So the point exists. That's 1 out of the 3 conditions done. The second condition then is the limit. Does the limit exist? Now, in this problem, we said that this is continuous. We said that this is continuous right here. Oh, and I do want to point out, I skipped this. I chose the point 1 because if this is always continuous and this is only continuous, the only spot where these piecewise functions are going to have a discontinuity is going to be at that point where these 2 functions are going to meet, in this case at 1. So what I want to do is I want to take the limit as x approaches 1 from the left side of f of x. Well, the limit approaches 1 from f of x when the x's are less than 1. So when I look, that is going to be the left side limit right here. So that's going to be 1 squared minus 3, which is -2. Now, we've already solved that, but you do need to make this limit statement. This, even though it's the same number, is not the same evaluation. I also have to check the limit as x approaches 1 from the positive side of f of x, or when the values of x are greater than 1. So in this case, I would get 1 minus 1, and I would get 0. Since the left side limit and the right side limit do not equal each other, the limit doesn't exist, and there's nothing else I can do. Now, we do need to verify this. I mentioned it in, I believe, BC. I don't think I've said it to AB. But when we do a problem like this, even though it doesn't say justify, it's going to be implied. In fact, last year is the first year that the College Board has taken the word justify and explain your reasoning off of every single free response question. It's now implied through the instructions. In the instructions it says justify and explain your reasoning for every question where that's required. So make sure that you're always putting a justification, especially if it's determined whether the function is continuous at the x variable. When they say that, that's a yes or no question. If it's a yes or no question, you need to make sure to justify it. In this case, you would say something along the lines, since the limit as x approaches 1 of the f of x does not exist, it fails at one of the conditions, in this case the limit not existing, f of x is not continuous at x equals 1. That's all you have to put. I'm stating my condition that there was failure, and then I'm stating after I look at my analysis, here's my condition that failed, and this is my final conclusion. We're always going to follow this idea of conditions. Make sure that we analyze the conditions to see if they work, and then make sure that we state it in a final sentence. So we look at B. Again, I've got another quadratic comparing to another quadratic. We know that those are continuous, so the only point that discontinuity could exist is in here when we've got x is at -2. So again, we do the same exact concept. We ask, what is the point? And we would say the f of, in this case, -2, the only location where discontinuity could exist is equal to 2 squared plus 3 times 2 minus 2. We go through, we find out what that's going to be. That turns out to be 3 times -2. That makes more sense. -4. So does the point exist? Sure does. Now why did I know to do this? Because there's the equal sign for this first line. Point number 2, limit. Here, I'll put a check right there. That's a little bit easier to see. So we do the limit. I need to check the left side limit. As x approaches -2 from the left. That looks really funny. Of f of x. We do the left side limit. That means that it's going to be -2 squared plus 3 times -2 minus 2 is -4. We also have to check the right side limit. Limit as x approaches -2 from the positive side of f of x. So that's going to be the -2 squared. -2 squared is 4, but multiplied by a negative gives me a -4. So the limit exists. So now I have to ask myself a third question. Does point equal the limit? And I don't really have to do any analysis because I can see right here these all match and we're good. So now I have to go through and I have to make sure to justify my answer. So I'm going to state, since f of -2 equals -4, and by stating that, I have told you the point exists. The limit as x approaches -2 of f of x is -4. And f of 2 equals the limit as x approaches -2 of f of x. Notice I've stated my point exists. My limit, there's 1. Limit exists. Boom, that's my 2. Point and limit are the same. That's my 3. You don't have to underline and number them. It's just stating, here it is. Since all of this, f of x is continuous. I do not have to prove that a quadratic is continuous. I do not have to prove my knowledge here, but I do have to prove at this intersection point that they are continuous. Last, but certainly not least, this last question, doing the same exact things, we're going to check for a point. The point f of negative 1 this time, because we're looking at negative 1. And there's a discontinuity here, but we're not equal to it, so we don't have to worry. We're not equal to in this discontinuity, where the discontinuity would exist, so we're never actually going to need that. F of negative 1 is 3 to the negative 1. That's cute, minus 1. So double negative, that becomes a 1. 3 to the 1 is 3. 3 minus 1 is 2. Cool. So now I check the limit. So let's do the limit as x approaches negative 1 from the left of f of x, which we know is going to hopefully be the same exact thing that we just proved. Let's check the limit from the right side. So I check the limit from the right side. I get 1 over negative 1 plus 1, which is 1 over 0. That means that that goes to infinity. Limit does not exist. So what do we state? We say since the limit as x approaches negative 1, f of x does not exist, f of x, I'll just write discontinuous this time, at x equals negative 1. That's actually all I got there, folks, is make sure to check those numbers. This is why doing the limit thing is so important, to be able to understand how to algebraically do a limit, because we're going to obviously do a lot of these as we go through. What I would like you to do then is taking a whole whopping 12 minutes of your life so far. That's not bad. What I would like you to do is on the next page, I would like you to do your best to answer the first question on this page. You've already got f of c is defined, limit of x equals c. You've got this. This is all nothing new. I would like you to answer this question. When you answer this question, well, actually, I won't even worry about that next thing. So I would like you to answer this question, and when you come in tomorrow, all I will ask is what you got. So hopefully this will help out a little bit on what we're looking at. That was the mechanical part. We're going to extend on this idea tomorrow. So hopefully that worked out. Hopefully you all have a good rest of your day, and I look forward to seeing you all tomorrow.